Okay, good morning, everyone. I want to welcome you to another statistical theory class. Of course, we started probability distribution of continuous random variable yesterday. We're going to continue from there today. Of course, I'm going to start from where we stopped. So I merge the remainder of the material for yesterday with what we're going to be doing today. So I'm going to start from where we stopped yesterday. Now, yesterday, like I said, I introduced you to probability distribution of continuous random variable. And of course, I remember I walk you through some basic properties of probability density function. So I'm actually going to kickstart today looking into example on how we can compute CDF from a given probability distribution. We can obtain CDF for both discrete and continuous probability distribution. The example I cited yesterday, of course, actually centered on continuous random variable situation where you have a discrete situation. How do we figure out the CDF? The CDF means cumulative distribution function. Now, you're given this, table. Okay, you see that table, right? In that very table, you actually have the value of a random variable with their corresponding probability. This is looking like a discrete case. Now the question is asking you to figure out the CDF. So how am I going to figure out the CDF? Of course, the formula for the CDF is actually, look at that. F of S is going to be an uppercase F. It is the probability of a random variable less or equal to a realized value. Now, what I'm actually going to do, just like the way we normally want to start, okay, we're going to start from this situation. Take a look at this guy now. You know, that is only talking about S equal to 0. Because if you look at the state space, 0, 1, 2. So if we want to start, we can do 0 less or equal to S less than 1. And I want to believe that is the same as X equal to 0. And what is the corresponding probability for that? It's actually 10 over 28. And after that, the next that we want to do, since we've done 0 to 1, it's going to be the turn of 1 to 2. Okay, 1 less or equal to S less than 2. Okay, now less than 2 means we're not going to be interested in 2. We're only going to focus cumulatively on what we've done before, S equal to 0 and S equal to 1. So that's why you see us writing that. So for S equal to 0, you have 10 over 28. For S, probability of S equal to 1, 15 over 28. And that's why you see us adding 10 over 28 plus 15 over 28. Okay. Now, lastly, we want to do 2 or more. 2 or more. And the 2 or more, we actually put into consideration adding all of that. And that's why you see this. S equal to 0, for S equal to 1, for S equal to 2. And that's why we're adding all of that up. Adding that up, that's going to be equal to 1. Don't forget, when I was doing it yesterday, you know where you're going to start? There's always going to be an extreme value, 0, 1, right? We got a 1 right now. Okay, this is another 1. This is to go against. I want you to take a look at these two things. 1 second. Look at this. Look at this guy. If you look at this guy and this guy, okay, those are the extreme. Where does it start from? Start from 0 to 2. But where if you're gonna start, we're gonna start from for less than 0, less than the lower point. That will always give you 0. Greater or equal to the upper part, that's always going to be 1. And that's why we're always going to have an extreme values, 0, 1. Okay. Now, after getting all of this, how am I going to put my distribution function answer? There's a way we're going to put that, which I need you to see right now. Now, can you see that? This is the way I want it to be. Look at that. Okay, you can see 0, 1. Okay, 0, 1 at the extreme. And for 0, 1, you are going against the domain, where every other one will now fall in between. This is the way we want the CDF to be presented after you've computed them out. Now, when we have a CDF, you can be asked to make a plot of the CDF. Okay, so what do you actually want to plot? Okay, now, if you take a look at this guy, okay, that is this plot. That is that. You see, from 0 to 1 is 10 over 28. Okay, then from 1 to 2, do you see that? Corresponding to 1 to 2, that is 25 over 28. Okay, and of course, greater or equal to 2, you see that guy, right? Greater or equal to 2. Okay, you see that? Greater or equal to 2 will correspond to 1. That's a CDF graph. Examiner can ask you to sketch the graph of a CDF. Okay, so please pay attention to that. Do you know from a CDF, we could have some computation too, like somebody asking you to figure out a CDF value when S is negative 0.5. Where does that fall? Negative 0.5 fall here, right? Then my answer is going to be what? 0. That's why I have 0. Okay, so CDF. So what this guy mean is referring to a CDF value when X is negative 0.5. Where does negative 0.5 lies? Okay, it's actually here. And that CDF is going to be equal to 0. Okay, so this is more or less like a piecewise function. Okay, now you could have look at another computation. They can ask you to figure out what is the CDF value. Okay, when S is 1.5, you want to figure out the CD. Oh my God, it's going to lie here. Okay, so that 1.5 lies in between that, right? Okay, my answer is going to be 25 over 28. Can you see that? Can you see that? So we can compute uh, probability with CDF. Okay, now I'm actually going to move. Now we're done with that. We want to go back to more examples on continuous random variable. Like here now, I'm actually showing you the real life application. Okay, on metal cylinder production. Suppose that the random variable S is the diameter of a randomly chosen cylinder manufactured by the company. Since this random variable can take any value between 49.5 and 50.5, it is a continuous random variable. When you want to work with a variable, you need to be able to identify what is the nature of the variable. Is it discrete or continuous? But because the diameter of a cylinder here, when they measure, the lowest bound they have in their measurement is 49.5, and the highest they got is 50.5. Now they derive a mathematical model, okay? Or the mathematical model on how that will enable us to compute the probability that the diameter will take a particular value within the interval. If you take a look at what I have right now, this is a mathematical model. You remember the other time when I was talking about probability model? This mathematical model is probabilistic. Probabilistic in the sense that it obeys Kolmogorov axioms. Kolmogorov axioms of, non-negativity. And at the same time, if I perform an antiderivative of this f of s, putting it across over the range of 49.5 to 50.5, I'm actually expecting the total area under a curve to be 1. And that make it a probability model. Now, you know what they are trying to tell you? They're trying to tell you the function, that probability function exists for cylinder if the cylinder measurement lies between 49.5 and 49.5 and 50.5. But this guy is trying to say it does not exist if the range takes otherwise. Does that make sense? That's what f of s equal to 0 means. Doesn't exist. It only exists, the model only exists, okay, within this domain. Okay, now, based on this, mathematicians have already done a great job giving us a probabilistic model that depicts reality. Now, can we have a way to sketch? If you want to generate a plot for this over this range, this is what you're going to get. It's going to look like a curve. Okay? Okay, so you can take some values, okay, and plug them in here and plot this guy over the range. This is what you're going to see. We call this a density plot. This is a density plot. Okay. Now, this is if I give you this, if I give you this guy and I ask you to investigate for its validity, investigate, because we could have, it is not all mathematical models or functions that are probability models. How am I going to know that this is a probability model? Then it must integrate to 1. That's exactly what I'm doing here. That's what I'm doing here. I'm performing an antiderivative over this range. And if the final answer give 1, then you're gonna start celebrating. That is a valid probability density function. Okay? That's how to investigate. And this is obeying Kolmogorov axioms. The Kolmogorov axioms of normalization. Normalization. That the probability of a sample space must be equal to 1. That's what we mean. Now, the moment this happens, we can conduct statistical inference. Okay, what if in a situation where I'm no longer interested in the entire range, I'm not interested in the entire range, 49.5 to 50.5, I actually want to truncate. Now, take a look at this question now. Find the probability that a metal cylinder has a diameter between 49.8 and 50.1. So which means I'm still going to perform an antiderivative, but I'm using the different boundaries now. At the end of the day, I got this. This is not surprising because I did not use the entire range. When I use the entire range, that will give me 1. But when I use a truncated range, then I'm expected to get something less than 1. And graphically, okay, graphically, this is what I mean. Oh my God. If I'm considering the entire range is going to be 1, but if I'm considering the shaded blue parts, I'm expecting something less than 1. You know, some of you've been hearing about probability, and you get scared. What is the meaning of this in real life? When I say, what is the meaning that I said, the probability that a metal cylinder we have a diameter between 49.8 and 50.1 to be this? If I want to interpret that to somebody that is not in mathematics or somebody that is not in statistics, you know what I'm going to say? I will multiply that by 100. You know what I'm going to say? I'm going to say performing this experiment 43.2% of a time, they normally have a diameter measure between 49.8 and 50.1. That's what it means. Probability represents frequency of occurrence. The number of times out of 100 they are able to record between 49.8 and 50.1 in diameter. That's what it means. Okay, now, any question on that? So far, so good, right? Okay, if you don't understand, please ask me question. You know, final exam is very close, right? Okay, ask me question you don't understand. Now, I want to move right now. Now, do you know I can also obtain a CDF, okay, from this given, when I started today, I actually show you how to obtain a CDF when you are given a table. Whenever you are given a table with a random variable and a probability, that would be for discrete. Okay? And I walk you through how to get a CDF for discrete. But how do we get a CDF for continuous? Of course, you have a continuous. Um, you have this particular f of s. This is a PDF. How do we get a CDF from a PDF? Please pay attention. How do we get a CDF from a PDF? What I'm going to do, I'm going to integrate this guy, but I'm going to go from the minimum to a particular x. And that is why you have this guy now. Okay. That's why you're going to have, oh my God, look at what you have. Can you see that guy now? Let me see. Okay. So can you see this guy? The CDF means the probability of x less or equal to a particular value, which means I'm going to go from the lower bound given. I'm not going to go to the upper bound. I'm going to terminate at a point s. Because I have x here, wherever I'm going to change, wherever I see x to something else, maybe to y or to t. Then I'm going to integrate that. I'm going to perform an antiderivative. Okay. And when I'm done with that antiderivative, then I'm going to plug in x. I'm going to plug in 49.5. At the end of the day, you're actually going to get your results. It's going to be in terms of x. That is why it is called f of x. The result is going to be in terms of x. Okay? The result is going to be in terms of x. And let me tell you this. If you want to calculate probability of x lying between a lower bound and the upper bound, the alternative way you can do is to go by CDF. And for of us get the CDF, then I'm going to do this. The CDF of the upper bound minus the CDF of the lower bound. Okay, that's an alternative way. If I don't want to go through the direct way, I need to get my CDF. And after getting my CDF, I'm just going to plug in 50.0. Then I'm also going to plug in 49.7. Then I'm going to subtract them. Okay, when I subtract them, then I'm actually going to get my results. Can you see that? So that is what I got. I got 0.39. Okay, got 0.396. That's what I got. Can you see that? Is there any question on this? Is there any question? Okay, now I'm going to move right now. Now that's how we do it. Now, these are likely questions. Maybe in the exam or in the assignment. Take a look at this. You were given this. Okay, you were given f of y equal to that. But you know what? This is not completely defined. You know why? Because k is a constant. So you need to first figure out what is value of k. For this particular f of y to be a valid PDF. So if I were you, you need to put integral, okay, k y 1 minus y, the y equal to 1. Then you're going to go from 0 to 1. Okay, I need to figure out the values of k for us. Okay, so if I bring k out, I'm going to have 0 to 1, okay, y minus y squared, the y equal to 1. Okay, then I'm going to perform an antiderivative right now. So it's actually going to be y raised to power 2 divided by 2, y raised to power 3 divided by 3, then from 0 to 1 equal to 1. Then you know what I'm going to do? I'm going to plug in 1, then I'm going to plug in 0. Okay, so when I plug in 1, I have 1 over 2 minus 1 over 3. Okay, of course, when you plug in 0, you're going to have 0 over 2, 0 over 3. Okay, everything equal to 1. So what you're actually going to have, finally is just you. Oh my God, you are back at what at maybe at a middle school or elementary school now. Okay, where you want to simplify that fraction. Okay, so 6. Okay, 3 minus 2, right? Okay, k to that equal to 1. So I'm having k over 6 equal to 1, then k equal to 6. Okay, you can see I just determine my k to be equal to 6. Whenever a distribution is not completely specified, and you need to first figure out the constants. And of course, you are actually figure out, the constants using the fact that, let me see if this is going to work. I think we shouldn't have any issue again, so it should work. Okay, it should work. Needed to work. Now, so I'm going to see it should work. Okay, so the law, this is the law. Okay, negative infinity to infinity f of s ds must equal to 1. Okay, so that's always what I'm actually going to do if I want to figure out the constants. Okay, now I'm going to go to the next question. Okay, I'm going to go to the next question. Like I said, if you don't understand, make sure you ask question, you pay for the service. Okay, now I'm actually going to go back into, where we stop. Now, you've been able to answer question A. How do I answer question B? That would be super cool. If I want to rewrite my answer, if I want to rewrite this guy now, okay, if I want to rewrite that guy now, my f of y will now be equal to 6y 1 minus y, because I just determined my k. Now it will be easy for me to find this. I needed to take a look at the B and C. B and C are the same in continuous. You remember I told you yesterday, okay, whether y less or equal to that or whatever, so they're going to be the same. So take a look at B and C here. Do you see B and C? With y when 4, 0.4 less or equal to y less or equal to 1 is the same thing as 0.4 less or equal to y less than 1. Or if they are both, they can be both less than, they can be both, less or equal to, they're all going to be the same. Okay? Now, what I want to do now, I'm actually going to perform, oh my God, that is easy peasy. I'm going to do 6y1 minus y, the y. Then I'm just going to do 0.4 and 1. I'm going to perform an antiderivative on that. Then plug in 1 and 0.4. I'm done. Okay? I'm done. That's how to do that. Okay, now another one that I want to show you right now. If you take a look at D and E, is there any different? Can somebody tell me, is there any different on how we're going to go about D and E? Is there any different? No, thank you so much. Now I'm actually, because I'm going to share my whiteboard, okay, I'm going to show you how you can figure that out. Okay, I'm actually going to show you how you're going to figure that out. Like I said, if you don't understand, ask me question. Now I'm going to share my whiteboard right now. So I'm going to share my whiteboard right now. I need you to pay attention. Okay, now I'm sharing my whiteboard, like I said. Now, I think our f of y, okay, our f of y is 6y 1 minus y. And what was the range? The range of y was between 0 and 1. Now, you want to find the probability of y less or equal to that, giving y less or equal to that. Please pay attention. What I'm going to use here, I'm going to use the idea of conditional probability. Okay, in the conditional probability, normally when you say probability of A given B, okay, what do we normally write? The probability of A intersection B divided by probability of B, right? Now my A, now this is my A and this is my B. Can you see that? My A is y less or equal to 0.4 and my B is y less or equal to 0.8. Now, what do I need to do right now if I really want to implement that? Now, if I really want to implement that, so like I said, this is acting like an A. This is acting like a B. Now, the first thing is going to be y less than 0.4, okay, intercept y less than 0.8. Look at what I'm doing first, divided by probability of y less than 0.8. Look at that. Is there anyone who doesn't understand how I'm interpreting that right now? Is there anyone who doesn't get that? Now, do you not know what we need to do? What do you think would be common? What is common between y less? I need somebody to tell me for extra credit. If you take a look at the numerator, okay, what do you think is common between them? No, no, I'm talking about this guy here. I'm talking about y less than 0.04, okay, and y less or equal to 0.8. What is the common point between them? You know what I mean by the common points between them. What do they have in common? The two of them. What do they have in common? Can somebody tell me? What do they have in common? What I'm trying to say right now is what is common between this guy and this guy. Okay, why do you say 0.4? They both have zero point 0.4. So let's see. If I have y less or equal to 0.4, right? And I have y less or equal to 0.8, definitely 0.4 is included. That's a good response. Is that what we're trying to say? Or something very close, right? Send me a message for extra credit. Now, if I want to rewrite that numerator, okay, if I want to rewrite the numerator right now, please pay attention. If I want to rewrite, the whole thing, I'm actually going to write this guy. divided by this guy. That's what I'm going to write. That's what I'm going to write. Because that's the guy is common. And what do you now think is the next thing to do? The next thing to do is integral. Okay, don't forget 6y, 1 minus y, the y. Now, this guy say, start from the lowest and end up in the 0.4. What was the lowest? 0, right? 0, 2.4. Then divided by 0, 2.8. 6y, 1 minus y, the y. Is there any question? You just need to perform an antiderivative, find the ratio, you're going to be done. Okay, I'm actually going to move right now. No, I'm going to move right now. Now that we have our probability in place, function in place, you know how to compute them, you know how to get a CDF. But right now, can we have some basic statistical measure aside that? Okay, so I'm going to move. Of course, I give you this an exercise. You can also try, but don't forget, this is a CDF. You need to get a PDF before moving forward. Okay. Now I want to move right now. Now, what is the essence of having a probability distribution function in place? The essence is so that we will be able to recover basic statistical measure. What are the basic statistical measure that we want to recover? Like mean, variance, standard deviation, and so on. But the implication, let me tell you this, before you can get a reasonable basic statistical measure, then you need to be able to ensure the validity of your probability function. I just show you how to ensure the validity. Now, we want to go into expected value. Expected value is the mean. How can I get a mean from a distribution? Now, I'm going to move right now. We call that expectation of X. Expectation of X means mean. And for a continuous random variable, the expectation of S for continuous random variable is this. Integral S f of S ds. Okay? Now, I'm going to go. Then what about expected value of S squared? Okay? Expected value of S squared is going to be negative infinity to infinity S squared f of S ds. So it's continue like that because I may want to get a variance. Okay, don't forget, if I want to get a variance, I need expected value of X and expected value of S squared. Okay, now I want to move right now. I want to go into example. Okay, I want to go into example. Now you're given this as a PDF, the PDF of weekly graph sales. Let me tell you this, mathematical models, probability models are very useful, not only in engineering, useful in medical field, useful in marketing and so on like that. Now, this is a mathematical model depicting sales, weekly graph sales. And S lie between 0 and 1. So when S lie between 0 and 1, maybe you are talking about the proportion or the percentage of gravel sale sold weekly, which is going to lie between 0 and 1, which means 0% to 100%. Now this is the F of S. I want to find the mean. Please pay attention. If I want to find the mean, this is the formula to find the mean. Then I'm going to plug in the F of S here. Then I'm going to use the range given. Okay. Then I'm going to perform an antiderivative on that. The answer is 3/8. You know what it means? On average, the weekly sales is 3/8. If I want to know, multiply that by 100. That will give it a percentage of graph sold a week. Any question on how we figure this out? You know, when you were in high school doing calculus, you may not know the essence of calculus. But right now, we need calculus. Calculus is live. want to take a decision, okay, probabilistic decision, where you're actually going to see yourself doing integrate, this is antiderivative, okay? Now, that's how to find the expected value of s. What of if I asked you to find expected value of s squared, okay? You can also do that. Now, for the expected value of s squared, can you see that? And after finding that, I got 1 over 5. You can try that, okay? You can try that. Now, why do I need expected value of s squared? Because I may want to find the variance. Don't forget, the formula for variance is expected value of s squared minus expected value of x or squared. And that's what I'm plugging in here. And my variance become that. And the moment I got my variance, I can get my standard deviation. I'm gonna find the square roots of variance to obtain the standard deviation. Okay, so this is the variance, and this is what I got for standard deviation. Just take the square roots of whatever value do you have in the variance. Any question? I think I put some exercise. Okay, take a look at that. I put some exercise. Okay, and you can also do something that has to do with linear combination. But let me tell you this. Let me give you a clue here. You know how to get this guy from this guy, right? How to get expected value of s, expected value of y. But if you take a look at question B define a new variable s in terms of y. How will you find the expected value of s? Expected value of s there is going to be 200. Expected value of y minus 60. But you've already gotten the expected value of y here. Plug that in. We can also figure out expectation of a linear combination. Take a look at that. Okay, so you can work on that. Now I want to move right now. Okay, now this is today's what I prepare for today. Okay, now we want to visit some common probability distribution of continuous type. We just talked about probability functions right now, but some of them have an household name. You remember when we're dealing with discrete distribution, we have some household name like Bernoulli, binomial, geometric, hypergeometric, negative binomial, discrete uniform. Now we also want to visit some brand, names in continuous family. And today we're going to be focusing on uniform and normal distribution. There are two types of uniform. Don't forget, under discrete, we did a discrete uniform. There's also continuous uniform. So what we want to talk about now is continuous uniform and also talk about normal. Okay, so let's take a look at that. Now I need you to pay attention. I want to talk about continuous uniform. Okay, now what is the PDF? Okay, if you take a look at this, the lower bound and the upper bound of a variable that follow continuous uniform is A and B. It could be A, we could have, they could be close at both ends. They could be open at one end, close at one end, or they are both open at both ends. They are the same for continuous. And what is the f of s? What is the PDF? Okay, what is the PDF? When I'm talking about continuous uniform, okay, when I'm talking about continuous uniform, okay, so this is the PDF. F of s is 1 over b minus a. The b is the upper bound and a is the lower bound. Okay, now the uniform is trying to say the probability of observing any event in the interval is the same. That's what we mean by uniform. Is the same. If I sell in a particular gas station, if I sell between so number of gallons and the other number of gallons, the probability of selling gallons, in the interval, any gallon in the interval is going to be the same. That's why it is called uniform. But you know what? We have, what does it mean? What is the variance? This is the expected value of S, and that is the variance. Okay? We have a way to show that. We can show that the mean equal to that and the variance equal to that. But you know what I'm going to do? Let me quickly show that. I'm going to show you the mean. You can try the variance yourself. Okay? I need you to pay attention right now. I'm actually going to show you that of the mean. Okay? Please pay attention. Okay? Now, if f of s, so if f of s is 1 over b minus a uniform, where s lie between a and b, expectation of s is going to be from a to b x. Okay, don't forget f of s dx. And what is my f of s? So a to b x. My f of s is 1 over b minus a dx. Okay, right now 1 over b minus a is a constant, right? I'm going to bring it out. Okay, I'm actually going to bring it out. Okay, so 1 second. Let me clean my whiteboard. Okay, so I'm going to bring it out. So don't forget, I'm doing this with the value of x. So 1 over b minus a, then I'm going to be left with this integral x dx. So let's perform an antiderivative on x. Okay, if you perform an antiderivative on x, what do you get? Okay, that will give you s squared over 2, right? Then from a to b, don't forget you have b, this guy here. So by the time you plug in 1 over b minus a, I'm actually going to get b squared minus a squared divided by 2, right? Mathematically, when I have b squared minus a squared, it's the same thing as b minus a, b plus a. So divided by b minus a, 2. What do I have? This cancel that. So what do we get now? Okay, we got the expectation of s is b plus a over 2. That is the expectation of s. So the expectation of a random variable s that follow a continuous uniform is just adding the upper bound to the lower bound and divide by 2. Okay, I will advise that you try expected value of s squared. Then you also try the variance. Okay, so that's how. Okay, now I'm actually going to go back to the material. I'm going to go back to the material now. So if you try the variance, this is what you're going to get for the variance. Okay, b minus a all squared divided by 12. If I were you, why can't you try that? This is what we just derived right now as the mean. Can we have a way to find a probability computation? Let's have an example on uniform. Let's have an example now. Suppose that x follows the continuous uniform, unif through 7. Whenever they give you a uniform distribution, you're actually going to be given the lower bound and the upper bound. So here, the lower bound is 2, the upper bound is 7. The first question asks, find the PDF of S. What is the PDF of S? It is f of S 1 over b minus a. What is this? Is b, this is a. A is 2 here, b is 7. So my PDF right now, f of s, will be 1 over 5. Done. A done. So the PDF is 1 over b minus a. So what you just need to do, identify your upper bound, identify your lower bound, then compute the evaluation. And that will be 1 over 5. And they say plot it. If you plot it, over 2 and 7, it's going to be the same. It's going to be horizontal because the probability is the same. 1 over 5. You 1 over 5 for whatever range of values between 2 and 7 when you plot it. Now, the second question said, calculate the mean. Mean is A plus B over 2. Here is going to be 7 plus 2 divided by 2. Done. Any question? And now we find the mean. Is it like question B now? Find the mean. It's A plus B over 2. A is 2 here. B 7. And find the standard deviation. Of course, you know, the variance is this guy. This is the variance, right? B minus A all squared over 12. So here is going to be 7 minus 2 all squared divided by 12. Whatever you get here, you find the square root. That will give you the standard deviation. Done. Easy peasy, right? Okay. All what you just need to do, you just need to figure out what is your A, what is your B. The moment you know your A, you know your B, every other moving forward will be so easy. Okay. Now, when you take C on uniform, still on uniform, okay, still on uniform, let's take a look at question C. Find the probability of S lie between 3 and 6. That is easy peasy, right? There you just do 3 to 6, 1 over 5 ds. Because your f of s is 1 over 5. How do I get that? It's 1 over b minus a. 1 over 7 minus 2. Then I'm just going to perform an antiderivative on this guy. Done. I'm going to plug in 6, plug in 3, then I'm done. Can somebody tell me how, if I want to get the probability of s greater or equal to 5, how is it going to be? Can someone tell me? Go ahead. Okay, 5 to 7, then 1/5. Send me a message for extra credit. Good job. I want to ask another question here. If I want to get the probability of s equal to 4, anybody? Probability of s equal to 4? Probability of s equal to 4? Hmm? Are you sure? Who can tell me? Probability of s equal to 4? It's going to be 0. Send me a message for extra credit. Because the probability that a continuous random variable will be an exact value is 0 all the time. So probability of s equal to 4 is 0. S equal to 100 is 0. S equal to you know what you can find here is the probability will exist if you're looking at the that in the interval. Does that make sense? Okay. I want to move right now. That is easy peasy. Okay. That's all about uniform. Any question about uniform before moving to normal distribution? Now I want to welcome you to another probability distribution of a continuous random variable. Normal distribution is one of the common, or it's an household distribution within statistical world. In fact, in the entire research world, okay, normal distribution is very, very popular. Okay, now the probability density function of a normal distribution is this guy. 1 over square root of 2 pi sigma exponential raised to power minus half s minus mu divided by sigma squared. So this is the probability density of a normal distribution. Now let me tell you this: the normal distribution was actually put forward by 3 scientists. It started with Bernoulli. It started with Bernoulli to Laplace, then to Gauss. Okay, so, but I'm not going to go into the history. I'm just quickly going to give you the shape of a normal distribution. How does it look like? Okay, a normal distribution has a double, has a bear shape. Okay, it is symmetric. The center is the mean. Okay, and of course, the deviation from the center can be measured by the number of standard deviation. Okay, most of the real life phenomena depict follow normal distribution. We want to talk about some biological process. We want to talk about, some real life phenomena. They actually exhibit this distribution. Okay, there are two parameters in a normal distribution: mean and the variance. Okay, so mu is the mean of the distribution that we call the location parameter. If I want to know the center, then I need the values of the mean. If I want to know how the data spread out, then I need the value of the standard deviation. Okay, so now before I go, because we're still going to start from this material tomorrow, I want to show you this possibility of having maybe you have three set of data. Maybe you have data set on income, you have data set on temperature, you have data set on height of individuals. There is possibility each of them could follow normal distribution. They could even have the same mean, but they're going to have a different standard deviation. So take a look at what I'm displaying right here. You know what happened here? How many shapes do you see? Three, right? They have the same center, but the way they spread differently. So this is a situation where they have the mean of 15, but the standard deviation is not the same. Okay. Oh my God. The one that will spread out the most will be the one that will have the biggest standard deviation. Okay. If I actually give you this particular shape right now, okay, the one with the biggest standard deviation is the one that is more spread out. If you take a look at this black curve, is the one with the smallest standard deviation. The one with the smallest standard deviation is going to shrink in. The one with the biggest standard deviation is going to spread out. Does that make sense? Now, I want to give you an example. There's possibility. You also have data set, three different data sets that have different center. They have this different mean, but they have the same standard deviation. This is an example. Look at that. Well, let's see the center. The center here. That is center for that one. The center for this one. The center for the other one. If you read it out, they have different center. And that was why this is the center 10, 15, 20. They have different center, but they have the same standard deviation. They are spreading the same way. Can you see that? So what are we doing right now? We're comparing different data set that follow normal distribution, that have the same mean, different standard deviation, or that have different mean, the same standard deviation. Okay, and we can also have those ones that have different means, different standard deviation. So tomorrow, I'm going to start from the properties of normal distribution. Is there any question for me today before I go? Is there any question? Make sure you all say same. Okay, some of you reach out about how some points were deducted in the grading. I think I put some the question, and of course I don't know. I think I've uploaded the solution. Did you see the solution to the midterm? You can check the canvas. If you don't see that, then I'm going to re-upload that so that you can compare the solution of the short answer with with what you got. Okay, so that's all what I got for you today. So until tomorrow, make sure you all stay safe and have a lovely day. Bye for now.